Okay, in this video we're going to give code to compute forward, backward, and centered difference approximations for derivatives. And the following code finds forward, backward, and centered difference derivative approximations for a given function for a range of delta values, then plots the absolute errors on a log-log scale plot. So we'll be using these three formulas to compute derivatives, and then plot the absolute errors, which is the difference between these computed values and the actual derivative. All right. So I'm going to put line numbers in. I always like to put line numbers, so I'm going to toggle my line numbers. All right, so first of all, we know that we're going to plot, so I need to include the magic statement. This is a Jupyter feature. You don't have to do this in other Python compilers. So matplotlib inline, so that just displays the plot in the Jupyter notebook. And of course we need NumPy and pyplot, so we'll do from NumPy import star. That will take all the functions from NumPy. And we also need from matplotlib.pyplot import star. So that will be our plotting functions. All right, so first, as usual, we have a section where we initialize the variables and the arrays that we'll be needing. So first of all, we're going to evaluate the derivative at a point for different values of delta. In this case, I'm using the point x equals 0.5. And then we have a function to be differentiated. So in this case, we're going to use the exponential function. So I'm going to take f equals exp of x, and this is the value of the function to be differentiated at this point where I'm evaluating the derivative. Now, to find the derivative, we want to compare this with the theoretical value, and from calculus you know the derivative of e to the x is e to the x. So here, this is the actual true value of the derivative that we're going to use to compare our results with. So I took this function and differentiated it, and since I'm evaluating the derivative at the point x, I need this theoretical value at the point x. All right, so let's get our delta values. We're going to be using different deltas, and what I'm going to be using 1/2, 1/4, 1/8, 1/16, and so on. So I'll call that vector delta x. Now, when I say 1/2, 1/4, 1/8, 1/16, that's 2 to the power minus 1, minus 2, minus 3, etc. So I'm going to take 2 to the power, and then to get minus 1, minus 2, minus 3, etc., I can use a range. So I'm starting with minus 1. Let me go down to minus 13, so I'll do minus 14 and minus 1. All right. So these are not choices you would know beforehand. I'm doing this for my particular problem. So when you do an exercise, all this information for x, f, and delta will be supplied for you. And given f, you should be able to compute the derivative. All right, so let's go ahead and do the calculation. First of all, we can do the forward approximation. And first of all, to do the forward approximation, we need to take f of x plus delta, and then subtract f of x and divide by delta. So I'm going to take f of x plus delta, I'll call it f plus, and that's going to be exp of x plus delta x. Now, this delta x is an array or vector of values, but Python can handle this just fine. It's going to compute exp of x plus delta for each of these delta values. All right, then the approximate derivative, I'll call forward, and that's going to be the difference between this f plus value and the f value, and divide by delta. So it's going to be f plus minus f divided by delta x. Right? Now backward is going to be similar. So because I'm lazy. I'm going to go ahead and copy this, paste it. This should be F minus. And instead of going forward, I go backwards. And this is going to be backward. All right, we'll have to change the order here. It's going to be F minus, F minus, F minus. But the delta x stays the same. All right, now to get the centered is the average of forward plus backward. So I'll say centered is equal to forward plus backward over 2. All right, so I have my 3 derivatives, which I computed using the array of values that I have for delta. So let's go ahead and compute the absolute errors. So the absolute error for the forward, we'll call that forward error, and that's going to be equal to the absolute value of the true value minus the approximate, so that's f prime, which is the true theoretical value, minus the forward approximation. Then I'm going to have backward error, and that's going to be absolute value of, let's see, f prime minus backward, and then I'll have centered error. And that's going to be absolute value f prime minus centered. Okay. All right, now I'm ready to display. So that's my next section. And I want to create a figure, so I'll do figure 1. Okay, that's my first figure and my only figure. All right, so I want to plot the forward, backward, and centered errors on a log-log scale. So the first is forward, so I'm going to plot. And I think I can do delta x and forward error. Okay, and then I want to add a label. So I have to, when I do the legend, so that's going to be equal forward difference. Okay, and I'm going to be doing the same thing for backward and centered. So I'll just copy this, paste it twice, and make my changes. This should be backward error. And this is going to be backward difference. And then let's make it consistent. And then this is going to be centered error. Okay. And then this is going to be centered difference. Okay. All right, now, so those are my 3 plots. So at this point, let me go ahead and test and see if I'm okay. So I'm going to go ahead and Control Enter. And let's see if I got a good plot. Okay. All right, so what mistake did I make here? Looks like I'm missing the divided by 2, right? That's pretty easy to fix. I think my key was sticky. Let's try again. Okay, still have a problem. All right, now, here it says integers to negative integer powers are not allowed. All right, so what's this talking about? Apparently, Python does not like an integer to negative integer values. So I can fix this easily. Just make this 2 into a floating point by adding a decimal point here. All right, so let's continue. See if it works this time. All right. And looking what we got a plot here. All right, so we haven't finished yet, but at least we got a plot and we got compiling. So let's go ahead and continue. So I want to set limits. If the problem asks for limits, if the problem doesn't ask for limits, you can just let Python set the default limits. So I'm going to set the x limits as 1 and let's see, I'll make it 1 e minus 4. Okay. So again, this is not something you would know beforehand. You might find limits by trial and error, or you might be given the limits in the problem. So y limit, and then this is, I'll say 1 e minus 9. and 1. So this is the left limit and the right limit. This is the left limit and the right limit. So this is going to actually reverse the scale. And let's do the log scale. So I'm going to do x scale log, and I'll do the same thing for y scale log. Okay. And then I want to label the plot and the axes. So I'm going to have an x label and a y label. And the x label is my delta x. Now I can use what you call LaTeX formatting if I use the $, just like you can in the Python, in the Jupyter Notebook. All right, this is going to print the mathematical symbol big delta. And the y label, on the y label it's going to be the absolute error. Okay. And then let me add a legend and a title. Now I already have the labels, so I just need to add the legend just by legend. And if I want to put in a particular location, if you want to know what location corresponds to lock equal 3, you can just type help parenthesis legend in the Jupyter cell and read the documentation. All right. So I have the legend, and then I want the title. Errors for forward, backward, centered, difference, approximation of, and then here it's going to be e to the x. Okay. And then finish with show, to show in the Jupyter Notebook. And let's see what we got. Beautiful. So lock equal 3 puts it in the lower left. And looks like I have a mistake here. Let's see if I can fix that. That's certainly not good. Forgot the $sign here. And let's see if we're better now. All right, so there's your nice, pretty plot. And should be enough for you to go and do the exercises for this section.